Hey there, man, it's Alejandro, and welcome back for day 92 of me doing the NeetCode 50 challenge. So today we're doing a very last LeetCode medium advanced graph problem, and without further ado, let's get right into it. Okay, today we get LeetCode medium problem 787. Ooh, like the plane, or am I wrong? Okay, cheapest flights within K stops. There are n cities connected by some number of flights. You're given an array of flights. Okay, n cities. Okay. Where flights of I is equal to from to indicates that there is a flight from city da 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 da. Okay, we are also given three integers source, des, and k. Return the cheapest price from source to des with at most k stops. If there is no such route, return -1. Okay. Okay, I thought this was going to be a bit more interesting. Like there's one of my favorite problems from computer science is okay. I saw cities and flights and I got excited. One of my favorite problems from computer science involves like not cities and flights, but like airports and flights and so on. And basically the whole problem is essentially it's like you're given a source S and a destination, like a source and a dest, and essentially you want to find the cheapest path from source to dest, and you must do so in the exact runtimes of Dijkstra's algorithm. And it's like, well, okay, bro, just run Dijkstra's. And it's like, one more caveat. You get at least one flight. Today's your lucky day. You can make it free. And the way you solve that problem is essentially you take the graph, you make a copy of the graph. For every node U, you make a node U prime. For every edge U to V, you make an edge U prime to V prime. And for every edge U to V, you make one from U to V prime of cost 0. And then you just return, you call Dijkstra's from this whole graph, and you try to find the shortest path from S to T prime, right? So that way it's like, anytime you choose to do a zero cost edge, you essentially lock yourself from the top to the bottom graph to essentially have locked in that free edge weight and so on, that free cost flight and so on. So then the shortest path from S to T prime is exactly what you wanted to do. And I love those types of problems. When I say that I love graph reduction problems, that just happens to be my absolute favorite one. I tried to actually submit that question to LeetCode, but I got ignored. So it's a little bit of a rip. But yeah, that's one of my favorite problems of computer science. It happens to be a DSA and algorithms problem, and it happens to be a graph reductions problem. So when I saw cities and flights and it's an advanced graph problem, I was like, oh my gosh, am I about to get what I think we're getting? But no. Okay, so this is a bit, well, okay, before I say simpler, let me relax. Maybe there's some issues that I think, but like, my intuition would be to run essentially UCS or Dijkstra's, and it's like, every time that you see a solution that involves, more than k edges, be like, ignore it, right? So essentially, we can try to do this right away. By the way, if you're not familiar with UCS, it's the exact same thing as BFS and DFS, where it's like BFS and DFS, the only difference is that you use a stack or a queue for either or. Stack for DFS and queue for BFS. UCS is the same thing, it's just so that you use a min heap, right, or a priority queue, and the min heap being based off the cost of a path and so on. And there you go. So what I would do is essentially it's like, what we'll do is we'll say our fringe, or our fringe we'll call is equal to a min heap, and we'll just have source cost number of edges. Node cost. Actually, we need cost first. Source. Num edges and node. Edge count. There we go. So here we'll do while length of the fringe is greater than 0, and here we'll need a visited set equals set, and here we'll have source at the very beginning. I'll say heap q dot heap pop from fringe. This will be cost comma edge count comma node. We'll do this. If edge count is greater, so it must be nk with at most k stops, right? So if edge count is greater than k, then just continue, right? If node is equal to dest, then we'll say return cost. Right, we want to return cost, right? At the very end, we'll just do return -1, right? Otherwise, what we'll do is hey, we need the neighbors, right? So what's flights? Is flights a bunch of edges? Yeah, from, to, and price, right? So here we'll just build an adjacency list. Step 1, build adjacency list with edge weights. Right, so here we'll say adjacency list equal to a hash map. I don't know if it's like labeled 0 to n, the node and so on. They probably are, but we won't assume that, so we'll just use this. We'll even do a default dictative list, and here we'll say, is it directed or undirected? From to I, so I'm guessing it's directed, right? So yeah, for from comma to, for source comma dest comma price in flights, we'll say adjacency list of source dot appends price comma dest cost comma node. Okay. Yeah. Otherwise, we'll say otherwise go through neighbors. For neighbor for price comma neighbor comma price dest comma price neighbor comma price an adjacency list of node. Then we'll do continue. Is this correct in like a shortest path problem? Okay, let me think. Otherwise we'll do heap view dot heap. So yeah, if neighbor not invisited, then we'll do heap q dot heap push into the fringe. We'll do the new cost will be, it took cost to reach this node plus price to reach this new neighbor node. The edge count will be edge count plus 1, and the new destination node will be what? Yeah, so here what we'll do is instead of this, edge count plus 1 less than or equal to k, less than or equal to k equals k. Visiting any neighbors would surpass instead. So here we'll just do continue, right? And then we can just do assert count plus 1 less than or equal to k is the point. If neighbor not invisible, he push fringe, comma edge count plus 1, and then the neighbor itself, right? Yeah. We gotta visit visited dot add neighbor. Seems like we're getting screwed. Yeah, here we'll do visited is equal to set. If node and visited, continue, visited dot add node. Because I'll have visited okay, okay. No, the point is that I'll have visited a shortest path. Yeah. Uh, yeah. We face this exact issue in Advent of Code. Uh, it's the problems with UCS. Yeah. Yeah. Oh. Yeah. Yeah. I get it. If anything, what I need to do is essentially increment, right? Where it's like we want to do it at most case stops. Cool, right? Because what's the time complexity here? N, where's K? Hundred squared. Yeah, that's fine. Number of edges. Yeah, we can only traverse all the edges once, which is totally fine. So if anything, what we want to do is not prevent ourselves from visiting an already visited node, prevent ourselves from going through an edge we've already seen. Yeah, and plus the graph is directed, so this makes it really nice and convenient, right? Instead of preventing us from seeing a visited neighbor, here we'll do visited edges is equal to a set. Yeah, if edge count is greater than k, yeah, when it says you can make at most one stop, it means stop here and go here, right? Source is 0 to 3. It's like, yeah, you can go here and here, right? Okay. K plus 1. Yeah. We'll just do it that way. Oops, logically equivalent to k plus 1 edges. Actually, it means one. So it's annoying. So like the last one doesn't count as a stop. So k equals 1 here is weird. I'm just gonna assume that k stops means that most k minus k plus 1 edges, right? There's just k stops in between. So you need k plus 1 edges, right? One stop in between means 2 edges. 2 stops in between means 1, 1, 1. Okay. I'm just gonna assume that that's essentially the wording here. Here we'll do max edge count k plus 1. Okay. Yeah, because here we'll do heap q dot heap pop every time. So yeah, so that way it's like, you know, we're guaranteed to have the smallest cost. In visited edges, continue. Otherwise, visited edges dot add node comma neighbor. In case there's like cycles in the graph. Yeah, this can be commented now. Fringe equals why am I node 2? Source is 0, right? Oh, I modify these values for source for u comma v u v price. Source comma dest or price. We'll do source comma dest comma price. Okay, so this works. Okay, let's submit it. And wrong answer. Rip. Rip, 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 rip. Okay, so it's 0. Okay. So source is 0, destination is 3. So we get to here to there, and you can do 2 edges. So you can do 1, 2, which is 6. Maybe I don't do something like this, right? Because I visit, yeah. So like maybe it's like I do this, this, and I visit the edge this way when I want to visit this edge this way too, right? So let me do print f string. Right, I bet you this edge has already been visited. Yeah, 2, 3's already been visited. Yeah, so this is what's holding me back. I actually don't want to do this. This is actually holding me back. Yeah, okay. Okay. Okay, so run this again. And submit. Oh, but now I might be too slow, is the problem? Yeah. If anything, I can do DP, right? I think something like DP will work, right? So here, def DP. Ooh, self.adjacency list equals adjacency list. Okay. Source equals source, right? So we have access to everything. Self, I need a current node. Otherwise, turn 0. If edges left equals 0, turn floor of infinity. All right. Otherwise, for neighbor price in this, we'll say, hey, self.dp from that neighbor node. Edges left -1. equals min of res, comma path cost. Path cost less than res equals path cost in res, right? Here we can just do source comma k plus 1. Okay, so DP works here. Is DP fast enough? It's a wrong answer though. I put no. Float of infinity, else negative 1. There we go. Yeah, okay, there we go. So float, yeah, okay, sure. But is DP fast enough? Okay, DP is fast enough. There we go. Bada bing, bada boom. Accepted submission, 34% and so on. Okay, but now we can clean things up. Okay. So instead of UCS, yeah. What's nice is, hey, DP is good for DAGs and so on. I don't know if this is necessarily a DAG and so on, but the fact that we're limited by k-stops is like, okay, we have a termination condition, right? So in terms of like, the subproblems themselves, it forms a DAG, even though the graph might have cycles, right? This is an infinite cycle, but the fact that you must limit yourself at k-stops makes DP a totally valid option. Okay. We definitely don't need something like this. Don't need this. Don't need this. Don't need this. Don't need no silver lining. So yeah, that way if I reach the same guy twice, and yeah, here we'll do node comma edges left memo return self.memo of node comma edges left. Memo of node comma edges left equals res, return res, right? Okay. There we go. Here we'll do self.test, self.memo equals des comma this. That's fine, we can have it all in one line. Okay, let's just submit this. Oh, that actually made us slower. Really, the memo makes us slower? Damn, okay, I'll get rid of it then. Thought that would have made us faster. Perhaps not. So I'll get rid of this. I'll get rid of this. So you're telling me this is faster? Okay, cache decorator is faster. Okay, sweet. Sometimes it is, sometimes it isn't. There we go. Was min of res for this. Turn. This might give me an empty arc sequence thing. I could have sworn you can pass in a default into a min function. Okay, it is. You can, it's just, it's being annoying. If anything, we can bring this down here. That way we don't need this way. There we go. Make it as confusing as possible. Yeah, there's no need for code golf here. Right, but then it's like, there you go, it's like, it's all working, it's like, here's my solution, but yeah, okay. Let's not do it this way. Let's keep it nice and concise in terms of code logic. There we go, sorry, that was just me messing around, having some fun, but no need to have unreadable code for literally no reason. And yeah. Okay, nice. Okay, there we go. Run one more time, submit one more time, and there we go. Bada bing, bada boom. We have a working solution. So there we have it. Okay, so as always in my videos, I do a quick recap if I was able to solve the problem. So for this one, essentially, this is just a classic shortest path problem where it's like, we're given like, an array of flights where it's like, we're given like, from a node to a node and the cost of like the edge to the, of that edge, right? So it's like, from to and the cost of that edge and so on. So we essentially are given all the edges as an array of flights. And so, and then we're given a source, a des, and a k, and essentially we want to return the cheapest path from source to destination as long as there's at most k stops. And k stops really means k plus 1 edges. If there's no such way to get from source to des and k plus 1 total stops, or k, so k stops, or which is the same thing as k plus 1 total edges, then return -1, right? And so this problem, I tried to do it first like, the UCS/Dijkstra way, and it turned out to be like, too slow. And so one way I realized that we could do it is just via dynamic programming. Now that I think about it, this might not be the expected way to solve this problem, because if the expected way, first of all, let's check off the fact that we did this problem. If the expected way to solve this problem was with dynamic programming, it would probably be inside of here. So maybe I cheesed my way out of this problem. Okay, so I might have to review how NeetCode did it afterwards, now that I think about it. But the way that I cheesed this problem is, okay, so essentially, dynamic programming, the way that it works is that in reality, all of what dynamic programming is just a directed acyclic graph, right? And so whenever you have a DAG in a problem, you can usually always, or can formulate the problem in terms of a DAG, you can usually use dynamic programming. In this case, obviously, we're not given DAGs, right? So it's like here, obviously, there's like a very clear cycle, even though we have directed edges. The reason why we can treat this problem as a DAG is because of this condition that we only care about paths that are at most k in length. So think about it. If you exhaust every single path that is at most k in length from the source, like, you know, there's only a finite many amount of possibilities of that way, even if there's cycles in the graph, right? So in terms of like, you know, the sub-problems that would ensue, right? Every single possible path of size k from the original source node, that will give you you know, a finite amount of possible solutions, right? And so the idea of dynamic programming is like, you know, try them all and return the best one, right? But try them all in an efficient way. Whereas like if you ever do repeated work, you know, recall the answer you got for a subproblem before to use it again, right? So it's like, you know, if I'm going infinitely in a if I essentially go here this is a bad example, right? But it's like, you know, I can reach this 3, right? And it's like, you know, let's say I have like one edge left, or if I did this and this and somehow I have like one edge left and so on, then it's like, okay, I'm doing the same subproblem. So let's see in terms of how I did it. Very first thing that I do is I build an adjacency list, right? So for every single like, you know, source, destination, and price and flights, I say like, okay, from source, you can go to dest with an edge cost of price, right? So it's very simple. So that way it's like, I can look at the adjacency list of source whenever I need to, right? And then what am I going to do? Okay, so I have a dynamic programming function that essentially takes a node to go from and the number of edges left, right? So the point of this problem is that you want to reach destination and you want to do so in the cheapest way possible, right? What I will originally pass into my DP function is source, right? Because we start from source, and how many edges do we initially have available? Well, k plus 1, right? So here, for example, number of stops we have available is k is equal to 1, and essentially with k equals 1, the best thing we can do is here, right? So essentially we do one stop at node 1, and then finally reach our destination, right? Which in total really means we can use a total of 2 edges, i.e. k plus 1 edges, right? If there was, if k was equal to 2, then we could go one stop here, one stop somewhere else, or we could do one stop here, and then finally reach our destination, right? So a total of 3 edges. So it's k plus 1 edges is how many you get, right? So at the very beginning, I essentially get k plus 1 edges to go from, and I have to start from source, right? And my end overall goal is essentially to reach my destination, right? So what do I do with this? Okay, I have a DP function, and all it says is like, okay, if node is equal to the destination, right? How much does it cost to reach destination? 0, right? Well, why? Because I'm already at destination, so to go from destination to destination is just 0, right? It's like, oh, you want to arrive to Miami. I am in Miami. How far until I get to Miami? You are in Miami. So you are in Miami, so it doesn't take anything to be in Miami. It's just return 0 if you're already at the destination. The point is to get to the destination. If you're already there, there's no price to pay, right? Otherwise, it's like, okay, if I'm not at the destination, it's like, okay, I must take at least, you know, one edge in order to get towards my destination and so on. If the amount of edges that I have left is 0, that means I cannot do anything more. So what I will essentially say with DP is that, hey, the cost of this path is infinity, right? And strictly there, and no longer looking at edges and so on. Because again, the point is that if I want to use an edge but I have no more edges, then it's like, okay, I treat this as like, you know, it's infinite cost because I cannot do this, right? The point is that I must do go find a shortest path from source to dest with at most k stops. If I want to use more than k stops, which is the same thing as k plus 1 edges, then I say I cannot do so. So I essentially say that the cost of that path is infinity, right? Here, edges left, remember, we start off with k plus 1 because we get k stops, which is the same thing as k plus 1 edges, right? So if the number of edges left is equal to 0, and we are about to use an edge because, again, we're not at the destination, then I just return float of infinity to essentially discourage this as being our solution, right? Otherwise, it's like, okay, I'm at a current node. I have at least one edge left, which, you know, I have a bunch of neighbors. Which neighbor should I go to? The style of DP is, hey, I don't know. So what do? You try them all, right? So here, what we're going to say is like, okay, for every single neighbor that we have inside of this node, inside of the node adjacency list, right? Essentially, it's going to have a price to essentially reach that neighbor. What we're going to say is like, hey, the cost of going to this neighbor and then, you know, finding the optimal way to reach destination, we'll just say it's like, okay, it's going to take price total cost to essentially reach that that neighbor node, right? And from there, what do we want to do? Well, we want to essentially reach destination from that neighbor node with one less edge than we had before, right? So it's like here we are originally at node and edges left. So for every single neighbor and price that we have in our adjacency list, we're going to say, hey, we're going to pay a cost of price up front right now, as well as the remaining cost from that neighbor with one less edge than we had before, right? So out of all the neighbor prices, I'm going to essentially say, okay, take the price of that edge and essentially recursively compute with our DP function, you know, the cost from that neighbor with one less edge to essentially reach the destination, right? And what I'm going to do is for every single neighbor in my adjacency list of nodes, I'm going to take the minimum of these, right? So for every single neighbor, I'm going to recursively compute the cost of like, okay, for each neighbor, I'm going to essentially take the cost of the edge plus recursively call my DP function to find the shortest cost with at most however many edges from that neighbor all the way up to destination, right? And how many edges do I have left from that neighbor? Well, I just took an edge to go from node to neighbor. So the amount of edges left that I have is edges left minus 1. I just used up an edge to get to neighbor, right? So I use one less edge. And that way it's like if I eventually go on with my DB calls, if I ever reach edges left is equal to 0, float of infinity is what I return because I didn't reach my destination, right? And then I'm essentially going to take the minimum one of these, right? Because many of them might be able to reach destination, right? It's just that some might do it faster than others, right? That's the whole point. So I take the minimum one out of all these. I don't know which neighbor to go to. So what do? I try going to every single one of them and return the best result, right? Note that if I have no neighbors, obviously there's going to be like, an empty sequence and so on. So by default, I say float of infinity to essentially say, okay, you cannot reach anything, right? Because if you have no neighbors, you can't go anything. So just return a float of infinity by default, right? And so that's why I have a default of float of infinity there by default, right? If you have no neighbors, then you can't reach destination. So you say, oh, float of infinity because you can't reach destination. So it takes infinity, right? So that way, what you do is you just call the DP function. You start from source and initially k plus 1 edges. And it's like, okay, if res is equal to float of infinity, that means there is no path without most k edges, so return -1. Otherwise, return result because it'll be the shortest path. And there you go, bada bing, bada boom. That is essentially the solution to this problem. And okay, I see that we're not maybe the most efficient, so there's probably a much more efficient way to do this problem. I'd have to think, because yeah, it is a bit cheeky, the fact that it did this with DP, just because yeah, what's K? Yeah, if anything, K is less than N, so it might be N minus 1. Yeah, and the edges and so on, this is N times K, right? On fourth and so on. So yeah, it might start getting a bit slow. But how would people do this faster, right? I don't know. I'm trying to decide whether I should look at how NeetCode did it just because I've already solved this problem, or actually legitimately think about how to do it, right? Because this is the point of the video where I've already explained how I did my solution and so on. So I'm kind of thinking what I should do here, right? There are entities. Yeah. I mean, I don't know. I've already found a way to solve the problem. So when I found a way to solve the problem, I'm like, done deal with the challenge. I think that's going to be my mentality, right? Kind of like in the last problem where it's like, as soon as I solved it with prims, I was like, oh, I don't feel guilty if I end up looking how to do Kruskal because I found a way to solve the problem, right? And so that, in terms of my lens, it's like, I passed the challenge, right? It's kind of like how in bouldering or rock climbing, it's like very personal. It's like in terms of 1% might consider just doing a touch is totally fine, or grabbing the top of the wall is totally fine and so on, but others might be no, you must hold 2 seconds and so on, It's in terms of what you think counts or not, right? To me, it's just if I was able to solve the problem with LeetCode, I consider that a win, right? Because LeetCode very much knows how to define the constraints such that it's okay, if they don't want an n-squared solution, they make n 10 to the 5 and force an O of n solution, right? So if you're able to pass a LeetCode problem, that means you pass it with the constraints that they put in place. So you've essentially passed the LeetCode problem, right? Even if you didn't do it with the optimal time complexity algorithm. Obviously, it's always fun to sometimes try to figure out how to do it as efficiently as possible, right? Because some problems contains duplicate, it's you miss the point of the problem if you did it in O of n squared time instead of O of n, but things like this, maybe it's a little bit more fine, right? In terms of I can still learn how to do it, but since I passed the problem and so on, I don't feel guilty if I end up looking how someone else did it. So you know what? Let's come over here and let's just, for fun, see how NeetCode solved this problem. Ooh, okay, so here he has a bunch of hints. Okay. Ooh, I see Bellman-Ford in here. Ooh, I might end up having to learn Bellman-Ford. Okay. Let's see, find cheapest flight. Well, Bellman-Ford is a DP algorithm, so maybe okay, Bellman-Ford, shortest path faster algorithm, n times k, and plus. Okay, so dexterous, find cheapest price. Okay, what does it do? Inf is equal to flow of infinity. Yeah. Adjacency list. Oh, he just used list, sure. What the heck is he doing? K plus 5? So he's an adjacency list. Is the source. Oh, so he just did what I originally did, but for some reason mine TLE'd. I guess his did not TLE. Okay. This is essentially what I had, it's just that mine time limit exceeded. Okay. Well, maybe they added some tests. Okay, then he does Bellman Ford, which is just the same thing, but I would have thought, like, something like Bellman Ford is slower, but maybe it's faster, just because it can adapt to this problem, right? I have to, I forgot how... Is the way that Bellman Ford works is that it's like up to k steps, and it's just like you do it up to, like, the total number of edges. Let me, what, I'm gonna grab my iPad over here. I'm going to grab my algorithm notes. Whoops. Okay. Algorithm notes. CSCC 73. By the way, these are like, all my, I'm literally at Bellman Ford. Okay. Low, that's lucky. 67. Okay, DP and shortest paths. Okay, so yeah, so okay, you can't really see on the screen and so on. Okay, Bellman Ford, single source shortest path of NM algorithm. All pair shortest path for Warshall, one of my favorite algorithms, by the way, just because I love the cool idea behind it. N cube, Johnson's algo, MN log n. Yeah, so obviously different between when the graph is sparse or not. So let's see. Okay, G this, define. Okay, wait. So how does Bellman Ford work? Bellman Ford does work in this way, right? So G is equal to, okay, define L of U K. Minimum weight of S to U path with less than or equal to K edges. Yeah, okay, so Bellman Ford is like made for this, right? Okay. It's just, I never remember how to write Bellman Ford. LUK. Yeah, so LUK is either equal to L of U and K minus 1, or L of UK and minimum V such that... Oh, and then he just proves that the algorithm is correct. Oh, claim 1 is that, okay, for all U, L, U less than K, L, U, comma, K, no label changes iteration. Okay, this is confusing. The way he writes was really, really hardcore. Okay, if G has no negative weight cycles reachable from S, it's logically equivalent to for all U, L, comma, U, comma, N is equal to U, N minus 1. So Bellman Ford claims that, like, okay, the shortest path from a node to another will use n minus 1 edges. Right. Yeah, okay. And so the way the algorithm works is L of S0. Oh my gosh, the way he writes this guy is really incredible. For K is equal to this, L changed. Yeah, geez. But yeah, okay. What I really care about is the recursive subproblem. So the point is that the shortest path with at most K edges is either the shortest path with K minus 1 edges, or if it has K edges, then it's going to be V K minus 1. Yeah, so you have to go through some minimum... yeah, this might not even be all this different, right? Because here I ended up going through like all of a neighbor that I have. Yeah, if anything, like, Yeah, okay. The way Bellman-Ford works, you either so the shortest path with at most k edges is either the shortest path with k minus one edges, or it's like okay, if you're at a node U, then essentially go to a node V with k minus one plus the price. Right? It's just that here. Here it's not really accurate for me to say like dp of node comma edges left minus one and so on. Yeah, if anything, it's like I kind of did like a super simplified version of Bellman-Ford that is just hyper specific for this problem, right? It's just that for some reason my solution is very, very slow. Okay, that's cool. That's a cool thing to know. So the way that Bellman-Ford algorithm, I didn't realize because out of the DP algorithms, I really love the Floyd-Warsh algorithm, and I will forever remember how that one works. So it's just so cool, like purposefully labeling the nodes from 1 to n and so on, 1 to k and so on, da da da. But okay, so it seems like Bellman-Ford, the way it works is that like you essentially build up like shortest path with less than or equal to k edges on and on and on and on until you do n edges, because that's like the maximal that would have been for the shortest path and so on. Makes sense, right? Because it's a DP based algorithm. Essentially by restricting a constraint like less than or equal to k edges, it forces it to be a DAG problem, which is exactly what I realized as I solved this problem without even realizing the connection to Bellman-Ford. So damn, okay, nice. Okay. And so shortest path faster algorithm. Okay, so like maybe there's some faster way of doing this. Okay, so some complexity and so on. Okay, but it seems like I wasn't way off, if anything, right? Bellman-Ford. I see, it just does one parsing of flights though. But it does so for all k plus 1 edges and so on, yeah. So the point is that you keep doing it for every edge and so on, da da da. It does a copy of the prices every single time and so on, da 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 da. And then it just sets them so yeah, I see. It's just interesting that like, this is, I don't know if this is actually faster and so on. But yeah, okay, so Bellman-Ford, the way it works, okay, kind of a cool idea. Yeah, you force something like less than or equal to k edges to force it to be a DAG, a problem that you can essentially do a DP type of solution for. And by the way, okay, like this guy, he's basically the king father of DP, right? So it's like we gotta respect the man. Okay, but yeah, it feels nice to figure out these things on my own. I definitely won't lie. So you know what? I'm proud of my solution. I will keep it as is. And there we go. Bada bing, bada boom. And this is nice, right? Because this officially means that now, we are finished with advanced graphs. And so it's fitting that we did this in a DP type of way, because what are we going to do now? We're going to get straight into the dynamic programming topic, which is probably going to be my favorite, or close second favorite, but my second favorite, if any, it would have been graphs and advanced graphs. So out of all the things remaining, we're getting straight into my favorite topic, baby, dynamic programming and so on. I know that like, a lot of people say like, oh, DP is scary and so on. I'm like, oh, my interviewer sucks, he gave me a DP problem and so on. Like, DP is the best one. DP is just brute force, but cache. It's like brute force, but put 3 lines of code to cache. Like that's it, and so on. So if and by the way, I think of problems in terms of a DP type of way. Anyways, I love thinking in DP and so on. Like in my opinion, it's actually like one of the most intuitive / simplest topics and so on out there. It's just like whenever you can think of DP, it's like it's awesome, and you can always rely on it and so on. The only problem with DP, the only disadvantage, is that for optimization problems, it's oftentimes the slowest algorithm, right? If you have a correct greedy algorithm for doing things, it's better, right? For example, shortest path traversals, right? Dijkstra's algorithm is always better than Bellman-Ford if you can afford to use it, right? It's just that you can't afford to use Dijkstra's when there's like negative weight edges, right? And so in those cases, like, oh, you must use something like Bellman-Ford and so on. But like, usually in problems where it's like, if there's a greedy counterpart type of solution, that's oftentimes the best. Or like, a good hybrid between greedy and dynamic programming is just like, divide and conquer, which is basically DP, but instead of the subproblems like, knocking off like a single digit one from a number n, it's like it like divides it by some value and so on. So it's like a nice counterpart. But yeah, so it's like trade-off versus Z's and so on. So greedy algorithms are harder to prove and so on. But like obviously, if you can write greedy algorithms are oftentimes incorrect, but like, if you can find a greedy correct algorithm, then it's oftentimes better than a dynamic programming algorithm. But dynamic programming, you can always rely on it, because what it is essentially just brute force. It's just that you end up caching. So like you can often turn problems from exponential time to polynomial time just because you cache results, right? And so that's the whole point of DP, and I personally love it. But yeah, so exciting stuff. But otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, ciao, my friend. Bye-bye.